Hi, I'm Camille from the University of the Philippines. Today, I'd like to share our study on well-dispersed YBCO and acetone. The performance of EPD in producing films relies on the quality of the suspension. Hence, our problem to address is to improve the dispersion stability of such suspension. Methodology. We applied two techniques prior to film deposition. First, planetary milling of the powder at different speeds, and two, using 5 mg iodine as additive to the suspension. Results. By simply milling the powders, we observed through XRD that the grain size reduced significantly. This is evidenced by the disappearance and broadening of peaks. YBCO acetone suspensions with and without iodine are also investigated. With iodine addition to the YBCO acetone suspension, the particle size shown by the black plots is seen to decrease and reach the minimum size of 250 nanometers. In terms of stability, all iodine-aided suspensions are found to be colloidally stable with zeta potential values of 43 to 45 millivolts. From here, we've shown that milling of powders and additive use have improved the dispersion stability of the suspension. For the final test, we have looked as well on the resulting as deposited films via EPD. As expected, the thin film deposited with milled powders have smaller particle clusters, compact particle packing, and uniform film thickness. Based on these results, milling the YBCO powder up to 800 RPM for 3 hours is enough to produce nano-sized YBCO particles with good dispersion in an acetone medium with and without iodine. Having this excellent dispersibility will allow the ultimate control of different as deposited film qualities. Thank you for listening.
I hope you are doing well. In behalf of my co-authors, I am here to present our study. In this work, we fabricate YBCO powder using soil process. We have prepared 4 samples with different pH of precursor solution from pH 4 to 7 to determine its influence in the composition of YBCO powder. In our results, the TGD-TA curve of dried aerogel powder of pH 5 sample shows 2 mass loss with corresponding endothermic and exothermic peak, which could be attributed to the decomposition of acetates and residual organic compounds. Another endothermic peak can also be observed at around 750 to 850 degrees Celsius, which suggests the start of the development of Y123 phase. To confirm this claim, all samples were annealed at 800 for 2 hours, and the XRD data shows that only pH 5 sample exhibits single-phase Y123. Whereas for samples pH 4, 6, and 7, the powders consist mainly of Y123 peaks with impurity traces of Y211 peaks. To further analyze the XRD, the volume fraction were calculated for all samples, and it is revealed that samples prepared at pH 7 is observed to have more impurities and lower yield of Y123 phase. The Y211 phase appeared at the sample prepared at pH 4 may be due to weak complexation of EDTA to metal acetates, because EDTA is known to be more soluble in water and not completely soluble at lower pH. This results to the precipitation of the precursor solution during gelation. On the other hand, impurities at higher pH of 6 and 7 could be possibly due to the excess amount of ammonium hydroxide, because the use of higher amount of ammonia could compete to EDTA for the complexation of copper ions, yielding to inhomogeneous distribution of metal ions. Furthermore, since samples prepared at pH 5 produce homogeneous Y123, it was also annealed at lower temperature for comparison, and it is observed that intermediate compounds such as the barium carbonate and copper oxide are still present at 600 degrees Celsius. This may also confirm that our annealing temperature at 800 is enough for the formation of Y123. For complete details, you may want to read our full manuscript 5G03. Thank you very much and keep safe.
Our paper is entitled Transport Properties of Indium Added Bismuth Strontium Calcium Copper Oxide or Bismuth 2212 thick films. In this paper, we report the effects of indium addition on the superconducting transport properties of Bismuth 2212 thick films fabricated by a sedimentation deposition technique. Here are the highlights of our study. Resistivity temperature measurements showed that the critical temperature Tc increases with up to 3 weight% indium addition. 1.5 weight% indium addition has the highest Tc onset of around 93.4 Kelvin, which is about 10 Kelvin higher than pure bismuth 2212 film. Critical current density, or JC measurements, show a twofold increase from 1.6 to 3.3 megaampere per square meter with 0.5 weight% indium addition. Comparison of morphology and transport properties suggests that the enhancement in TC and JC are due to optimization of charge carrier concentration and improved surface morphology. In summary, indium addition at small amounts can positively affect the superconducting transport properties of bismuth 2212 films. Our results include around 10 Kelvin increase in Tc with 1.5 weight% indium addition and a twofold increase in JC at 0.5 weight% addition compared to pure bismuth 2212 films. The enhancement in Tc and Jc are attributed to the optimization of charge carrier concentration and improved surface morphology of indium-added bismuth 2212 films.
Substance identification by trace analysis is the primary step towards the address of water pollution due to industrial waste dyes. It is achieved with SIRS by enhancing the characteristic Raman signal or fingerprint of a trace substance using nanometals. This study aims to identify the optimal source condition using silver nanowires and a dye called methylene blue or MB for an efficient and cost-effective source protocol. A 5x4 source matrix with increasing MB concentration and increasing nanowire volume was produced by depositing the nanowires on a glass slide via the Dr. Blade method and by drop coating the MB over. The substrates are then characterized by Raman microscopy. The faint signal of MB was enhanced to 10 to the 4, while MB peaks were redshifted in the source spectrum. These observations imply the activity of the electromagnetic and chemical enhancement mechanisms. With constant MB concentration, the source intensity increased with the nanowire volume due to the introduction of large amounts of hotspots that facilitate electromagnetic enhancement. It became saturated at the 150 microliter nanowire volume due to the frequent addition of nanowires. With constant silver nanowire volume, the source intensity increased with the MB concentration due to the increase in the MB molecules engaged in the source enhancement. To better approximate the source behavior, the data was interpolated into a surface response plot. The intensity gradually increased and peaked at 425 micromolar MB concentration and 156 microliter nanowire volume, which are the optimum parameters for the best source enhancement. With this in hand, the source efficiency, reliability, and productivity is maximized as a potential standard protocol.